So this is a summary of the priority. And in this sense, we must restructure the control tasks. Not as we saw at the beginning. First take all the data, then compute, then send, and then update and wait for the next. This is not the right way to implement a control algorithm. Because scheduling and network parameters influence the task timing parameters, latencies and jitters. And then they also influence the control performance. And these are very complex relationships. Some people, mainly in control, but also in computer engineering, they have tried to look for these relationships, but really they are very complicated, and the best solution is to have secure actions and backup activities better than try to prevent all the situations. So in general, sampling has a negative effect. Short latency is better than a long latency. But if the latency is known, we can take this latency into account in the control algorithm and then counteract this latency. The problem is if the jitter is very big, and from one time to the next, we have different operating conditions. Then this can be very bad for the control performances. However, some anomalies exist, and I have been dealing with this in some papers. As I mentioned at the beginning, that sometimes the delay can be beneficial for the control. Not always. I remember once giving a course to PhD students, then I said, well, for tomorrow you must do that exercise and look at the influence of the delay. This was, I must confess, 11 years ago. And one of the students came and said, well, professor, if I introduce the delay, the response is improved. And I said, well, go home and repeat the exercise because you are wrong. Well, I realized that he was right, but I posed the same question to many colleagues in control, and the first reaction was the same. This is not true, but really it can be. So it's not the normal case, but some cases can be different. So then one of the concepts I want to introduce now is the control effort concept. What that means? So if we have a loop in controlling and we introduce delay, this delay can influence more or less the control performance. As much the control performance is influenced by the delay, the most relevant this signal is. If we have a motor which time constant which is 10 milliseconds, we want to control and give a time constant of 9 milliseconds. If the control fails, instead of 9, we get 10, which was the original. But if we want to go from 10 milliseconds to 0.1 millisecond, that means that we are doing a lot of control effort. And if this control is not properly applied, and properly means delayed by some activities the computer is doing for some other reasons, then we are in trouble in the control. So this is a very illustrative example. We have here a reactor, and we have many signals. Temperature measurement, concentration measurement, valves to be controlled, and so on. And then we make a design. I don't want you to know about that. Simply is that we have this system, and we have a computer to control this plant. So which are the most important signals in this plant? First of all, we must see what happens if one of the signals is open and if the rest are active. And we will give the highest priority to those signals which are degrading most the behavior of the plant. So if everything is running perfectly, the plant matches the performance, the requirements. But if some failures are more relevant in the sense that the performance are degrading more, these are the signals we must give the highest priority to deliver and to acquire. So we have new control scenarios, embedded control systems, network control systems, and event-driven control that I'm going to consider briefly. Embedded systems, you know, they are everywhere, and the interesting thing for us is that control is present in 99% of the embedded applications. Anytime that there is an embedded application, mostly they deal with control. And embedded systems are devices which are embedded in a general one with compact and reduced size, autonomy, should deal with missing data, should deal with faults, and allow reconfigurability and safety of operation. So in the case of control, it's even more. They are information processing systems embedded into a large product, but the main purpose of the product is not information processing. It's a car, it's an aircraft, it's any process. And this embedded system should be dependable, efficient, interactive with its environment, real-time constrained, and application-oriented. So the main issues refer to embedded software. When we talk about embedded systems, we are not talking about microelectronics or mechatronics, which could be also the case. But the most important is that we are dealing with software, embedded software. And the most usual requirements are that they are reactive systems, the consumption of energy and the adaptation to the changes in the environment, and in many cases they are just pure control applications. So it's a strong interaction between the control and its software implementation. So we can say that embedded control systems are embedded systems with hard real-time constraints, but what is more important is that they should guarantee safe operation. And they should provide, in any case, the best possible performance, without S, the best possible performance. So let's have a look at the implementation of these systems. Embedded control systems, for us, is very interesting because they join computer real-time issues, networked systems, and control under uncertainty. In the middle of all these are the embedded control systems. And what are the main characteristics? They have limited computing and communication resources. So the easy solution we mentioned at the beginning, just buy a faster computer or just add some extra resources, is not anymore applicable. And also that they should have autonomous operation. There is no human operator. They have a complex functionality, and in general they have large amounts of software. And they need for formal design and validation approaches. In the case of networked control systems, we have more and more this situation. We have different nodes, and these nodes may be just a full process, or it could be just sensor or controllers generating control actions and so on. So the idea is that when we have many components distributed and connected in network, then we must identify which control task should be allocated to each one of the nodes, and we must identify and share information between all the nodes, and we must schedule the task for each one of the nodes. And there are some drawbacks. First, that most of this activity is offline, so in general they are too rigid. If we want to be in the safe side, then the resources are infra-used, and we must overestimate the delays. So is in general, to be sure that the networked control system is properly operating, we are requiring very poor performance, very conservative. And there are a lot of improvements, but most of them are under development. Event-driven control is a different approach of controlling. We have the process here, the sensor, the actuator as before, but here instead of sending the information continuously, we are detecting an event. So instead of sending data, we are detecting that an event is happening, and then the event processor will determine what to do to the control action generator, and then this will generate and change the actuators. So if there is no event, nothing happened here, and we can use the computing facilities for other activities. As far as there is an event, we must update the control. And as I mentioned, this is very appealing, but it's also very complicated. This is quite natural in networked embedded systems. When you have many nodes, so not all the nodes should be working at the same time, doing the same, and they should be excited or fired by signals, which are the events. And then also modes are changing continuously. We may have binary sensors, and all this is very, as I mentioned, complicated. This is an application we have developed here. Is a crane, and we have here the load. And instead of sending the position of the load continuously, we have here some cells, and we send the information anytime we cross that. That means that in practice, in many applications, you already have some sensors or some actuators which are event-based. They are not time-driven, but event-driven events. So after all this panorama, we can see that all the scheduling of the control implies temporal non-determinism. Because we are sharing the resources, we must do different activities and so on, and also in the case of networked control systems. So how should we handle this? Well, we must do as we have been doing till now, separation of concern, assuming everything is regular, but as I tried to forward to you, this means low use of resources, or we can integrate and take into account both, and design the system based on the resources availability. So, taking into account resources constraints, the goal of the temporal design methods is to maximize the control performance by maximizing the time determinism, making a robust design, or what is most important, prioritizing control subtasks. And this will be done by the control kernel that I'm going to talk about next. So these are the real-time constraints that all you know. I'm going fast. And from the control point of view, we must use reduced order models, non-conventional sampling, and a number of issues that I will go in detail here. For instance, we have this process, and this process can be split in different parts. We have sub-processes. And then we can control this as the fundamental part of the process. And if we have more time, we can use the other signals and implement the full control. So model reduction deals with partial control, parts of the plant, as you can see in this block diagram. Or we can deal with partial phenomena, fast or slow dynamics, and then use a reduced model of the process depending on the conditions. Here is an example. Assume that you have a mobile robot, and this system is also performing some activities here. And you want to move from one initial point to an ending point, and you have some obstacles here.